In this chapter of locational marginal pricing, we'll be considering offer-based economic dispatch. First, we'll have an overview, then a review of the definition of surplus. We'll discuss the feasible production set, the need for centralized coordination by an independent system operator, optimization formulation, the form of generator offer functions, the demand side, both specification and bids, how the ISO, or independent system operator, calculates the dispatch and prices the energy transactions. We'll discuss the incentives provided by those prices, and then in later parts of this chapter discuss various generalizations to ancillary services, including reserves and regulation, to nonlinear system constraints, and also we'll discuss more generally the representation of constraints. There are some homework exercises at the end. So first, an overview. We're now going to begin to synthesize the background material that we've met in previous chapters in the context of offer-based economic dispatch. We're going to put together, finally, optimization, economic dispatch, and markets. In Chapter 9, we'll also add transmission constraints. So this chapter will consider electricity markets without considering transmission constraints. And we'll see that offer-based economic dispatch will involve submission of offer functions, offers for short, by generators or their representatives, specification of demand by consumers or indeed by their representatives, or a specification of their willingness to pay, which is the counterpart of the offer. And then both of those items submitted to the independent system operator, who uses the offer functions and the demand information to choose the dispatch of the generators, to meet the demand, and to set the prices. Offer-based economic dispatch is a type of auction, by which I mean a set of rules, or sometimes called a mechanism, that takes offers and bids and calculates the quantity sold and the prices. There are a whole lot of types of auctions, and they have various forms and properties in various contexts. Our particular auction, offer-based economic dispatch, is designed to result in dispatch and prices that would be consistent with what we would have seen in the equilibrium of idealized bilateral trading. We'll see reasons for why we can't just rely on idealized bilateral trading in practice. We'll also discuss the criterion for choosing the dispatch. It will involve maximizing the surplus, properly speaking, the revealed surplus, meaning what is revealed by the offers, over or while satisfying the constraints implied by the feasible production sets of the generators, and where we have flexible demand within the feasible levels of demand. In this context, we need to face an issue, which is that the ISO is behaving as a central planner, which in some of the earlier chapters I indicated potentially had some drawbacks compared to an ideal market. So it's certainly the case that the ISO behaves as a central planner for short-term operations. But in principle, the ISO is applying a well-defined algorithm or mechanism. In other words, it takes offers and demand as input, provides dispatch and prices as output. Having said that, some initial proposals for restructured markets involved a smaller role for ISOs than we're going to discuss. But as we will discuss in more detail in section 8.4, because someone needs to centrally coordinate the matching of supply to demand in real time, it necessitates some version of system operator that has some central operational planning authority and some operational authority. So to a definition of surplus. It speaks to what we're trying to achieve with electricity market design. And as discussed in Chapter 7, one public policy goal is to maximize the benefits of electricity consumption minus the costs of electricity production. So let's define that. The surplus, sometimes called the welfare, is the value or benefits of consumption minus the costs of production over a particular time horizon. This is similar to what we used and discussed for the apartment example and is simply a restatement of the definition that we made in Chapter 7. We need to assume, since we're subtracting costs from benefits, that they can usefully be compared using, for example, monetary units. In the context of electric power, surplus is the value of benefits of electricity consumption minus the cost of electricity production, both measured over a particular time horizon. Surplus is therefore denominated in monetary units, or monetary units for the duration of the time horizon, or in some cases we'll think of it as monetary units per unit time. It of course depends on the demand power consumed by the load and the production of the individual generators. For short-term operations, the costs are mostly operating costs associated with fuel, natural gas, coal, and together with variable maintenance costs. And as I alluded to a moment ago, in shorter time contexts, instead of thinking of the surplus per unit over the time horizon, we think of the surplus as per unit time, in which case we're really considering the rate of change of surplus with respect to time. We're considering the surplus per unit time. I'll be a little bit non-specific when I use the word surplus. It could refer interchangeably to either surplus, a total amount of dollars, or a total amount of dollars in a particular period, or sometimes I'll really be meaning surplus per unit time. Regarding demand, in some cases we'll be specifying the demand as a fixed desired value, let's say D over line, that needs to be met by supply if that's possible. That's to say the demand is inelastic. In the cases of inelastic demand, the benefits of demand are not really explicitly revealed by a response to price. They're somehow implicit. And as in section 7.8, the derivative of the benefits with respect to demand, which we call the willingness to pay, is in this case assumed implicitly to be something like positive infinity, or at least a very large positive value, let me call it W, for demand in the range from 0 up to the specified desired level of demand D over line. And then it doesn't increase with increasing demand, let's say. However, when we're not explicit about revealing the benefits, we'll see that there are difficulties. For example, discussions of reliability of the electricity system often make the implicit assumption that the derivative of benefits, this number W, this willingness to pay, is extremely large. We'll see that that occasionally results in prices rising to this value, but we may set up our market process in a way where we simply don't charge for consumption on this basis. This can result in a serious discrepancy between the returns on investment for generation. There's simply not enough from the remuneration from consumers. And if you think back to section 7.8, we had a necessary role of demand setting a high price during curtailment in our description of the idealized market. This is really the core of the current concerns about capacity adequacy in ERCOT. To deal with this, in some cases, we'll posit an explicit form for the benefits of demand, even if in practice there isn't an explicit demand bid, in order to understand what would have occurred in the idealized situation, in order to understand what should be a proxy. Turning from surplus to the feasible production set, implicit in the definition of surplus is the assumption that we're choosing the production of generators from a feasible production set. That feasible production set is determined by constraints such as demand-supply or supply-demand power balance, and generator capacity constraints, which we've already seen, and transmission constraints, which we will treat in Chapter 9. As discussed in the context of economic dispatch, we're going to make demand-supply power balance explicit for the energy produced over each time scale that we consider by requiring that the average supply over a particular pricing or dispatch interval equals the average demand. So let's say the dispatch interval has duration T. T could be an hour, and in which case we'll be requiring that the average supply in the hour is equal to the average demand in the hour. The decision variables represent averages over the dispatch interval. Of course, as we discussed in the context of economic dispatch, demand-supply balance must be maintained continuously. The need to maintain supply and demand continuously is met in the short term by ancillary services. Power balance constraint and transmission constraints are examples of system constraints. The generator capacity constraints are examples of what I'll call generator constraints. Unlike the apartment example, which we met in previous chapter, each landlord had a single indivisible apartment to rent. Unlike that case, each generator can produce and sell over a continuous range. Each generator can sell anything in the range specified by its capacity constraints. So that representation gives us the generator constraints. Well, I just brought up the apartment example, and this is a good opportunity to discuss the need for centralized coordination. Because in the apartment example, there was no centralized coordination of leases. Individual landlords and renters could come to an agreement. They had enough time between successive months to negotiate price in a bilateral month-to-month rental agreement. It was assumed implicitly that renters could be evicted when an agreement expired, so the bilateral contracts could be enforced by landlords, and either an apartment was rented for a month or it was not rented. It was indivisible. Furthermore, the demand and the supply functions for apartments were assumed to be fixed, or at the very most they were slowly varying. We found that there was a single market clearing price for all apartments, and that arose somehow automatically as a natural outcome of self-interested behavior by landlords and renters. In practice, the price might adjust over several months towards the equilibrium, but it didn't need central coordination. Electricity, however, is rather different. The demand of individual consumers varies continuously, and at least for the foreseeable future, is mostly price inelastic, in part because of a historical lack of interval metering. Stoff calls the lack of metering and the lack of retail billing the first demand side flaw. Having said that, residential interval meters have been installed throughout ERCOT and are in place for all large customers, which means that we should anticipate gradually more and more customers will be exposed potentially to real-time prices and to the implications of those real-time prices, which includes potentially greater price elasticity. But furthermore, the transmission system links all supply and demand collectively. We have to meet total supply has to meet total demand, meaning typically the total supply has to be deliberately controlled to match total demand. Otherwise, we'd have widespread blackouts. Bilateral contracts in electricity cannot be enforced in real time, at least not very easily, since individual customers cannot be cut off if their demand exceeds their contractual quantity, or if the demand exceeds a contractual maximum, or if a customer violates some other contractual condition. It's typically not easy to do that. Stoft calls the lack of real-time control of power flow to specific customers the second demand-side flaw. Because of these characteristics, we just can't avoid central coordination. We can't simply only rely on bilateral contracts between generators and demand, or even between portfolios of generators and aggregated demand. Because of the lack of real-time control, a system operator needs to be there to step in to be the default supplier in real time to match supply and demand to avoid widespread blackouts. There's just no analog of widespread blackouts in the apartment renting example or indeed in other commodity markets. If there's a problem between supply and demand between a particular landlord and renter, they resolve it without necessarily affecting the wider economy. In electricity, a failure to meet demand means a widespread failure, which can lead to widespread blackouts. Furthermore, when supply and demand doesn't intersect, when there's just not enough generation, the system operator needs to deal with this case, and in extremis needs to arrange for curtailment of demand when supply and demand don't intersect. Again, there's no analog of the active need to maintain supply-demand balance across the whole economy. There's no analog of that in the apartment renting example, or indeed in other commodity markets. The reason is total apartment supply equals total demand, since individual landlords enforce each individual bilateral contract. But this simply isn't the case in electricity markets. So to summarize, the system operator is necessary in electricity markets for matching supply to demand under normal conditions and curtailing demand to match supply under extreme conditions, and when those extreme conditions occur, setting the price. To carry out this role, the system operator should be independent of market participants. It should be the independent system operator, or ISO. There are other roles of the system operator. For example, demand changes quite rapidly and varies continuously. It's pretty hard for individual generators and demand to rapidly adjust prices and establish an equilibrium through bilateral contracting when demand changes rapidly. So the system operator can facilitate the efficient use of generation by explicitly seeking the market clearing price based on the offer and bid functions. In the ERCOT zonal market, that was in place in ERCOT until December 2010, there was short-term adjustment of supply to meet demand through ancillary services. Ancillary services were procured in a day-ahead ancillary services market run by the ISO. There was a real-time balancing market that had a duration of 15 minutes that arranged for matching of supply to demand on a 15-minute by 15-minute basis. And in addition, longer-term decisions were taken through bilateral contracting. In the ERCOT nodal market, short-term adjustment of supply-demand also carried out through ancillary services, but that is only for things that happen below the 5-minute dispatch intervals of the real-time market. There's a day-ahead market which has 1-hour dispatch intervals, again run by the ISO, that also includes unit commitment decisions and ancillary services. But again, even longer decisions were taken through bilateral contracting. When transmission constraints bind, it's especially difficult for decentralized decision-making through bilateral contracts to achieve efficient generation dispatch. So the role of the system operator is particularly important when there are transmission constraints. In the ERCOT zonal market, interzonal transmission constraints, there were about 4 or 5 zones, differed from year to year. The transmission limitations on transmission lines between the zones, the interzonal constraints, were managed by ERCOT as another function of the balancing market, that is in addition to maintaining supply-demand balance. The intrazonal, or internal to the zone transmission constraints, were managed by ERCOT out of market. In contrast, in the ERCOT nodal market, both the interzonal and most of the intrazonal transmission constraints are managed in day-ahead and real-time markets. Some constraints are still managed out of market through a process called the reliability unit commitment, but by design, more of the transmission issues are handled within the market process. So let's put this into an optimization formulation. As we've discussed in section 8.2, maximizing surplus for electricity over short term, assuming that unit commitment decisions are fixed, is the process of economic dispatch. Offer-based economic dispatch is where the ISO solicits offers from generators, forecasts demand or solicits a specification of demand or a specification of bids, finds the market clearing prices and quantities with the goal of maximizing surplus. In the next sections, we're going to describe the offers, the demand, and the formulation of the optimization problem. First, the offer functions. Remember from section 5.3.4, that if the price for energy is specified and cannot be influenced by the generator, then we argue that the generator does best, maximizes its operating profits by specifying its offer function equal to its marginal cost function. So that is to say, under suitable assumptions, the offer function will equal the derivative of the cost function. Fk is the generator cost function. The offer will equal the derivative of the cost function with respect to, let's say, generation. I'll write that as the gradient of Fk. In some of our generalizations, we'll think of Fk potentially depending on other issues besides generated power. In practice, market rules typically restrict the form of the offer function to being piecewise linear or piecewise constant. In this case, the offer function may only approximate the marginal cost function. It won't be an exact reproduction. Furthermore, since the offer is assumed to reflect a convex cost function, market rules require the offer function to be non-decreasing so that the corresponding cost would be convex. So from now on, we'll assume that offer functions are specified equal to marginal costs. We'll revisit this in section 8.11 briefly. Furthermore, for now, we'll assume that the generation of a generator that is in service but not producing any net power. We can think of that as Fk of 0, although to emphasize that it's in service, I might write it Fk of 0 plus, meaning the limit of the costs as the net production goes to 0. For now, we'll assume that that cost is 0. That means that we could reconstruct Fk from its gradient by simply integrating. If we needed to calculate Fk at some pk, we'd integrate from y equals 0 up to y equals pk, the gradient. In more general cases, Fk at 0 plus might be not equal to 0. In other words, we'll have auxiliary costs. And we'd need to add these no-load operating costs or auxiliary costs back in to the expression to evaluate Fk of pk. However, for now, with unit commitment decisions fixed, and so therefore we're considering economic dispatch, the optimality conditions for economic dispatch only involve the gradients of the Fks. They don't involve Fk, so that the ISO doesn't need to evaluate Fk to solve the optimality conditions for economic dispatch. However, when we turn to unit commitment, we're going to see that in order to discuss costs and make whole payments, the ISO will indeed have to evaluate Fk. And at that time, we'll have to be more careful about the fixed costs or no-load operating costs. If the benefit of consumption is implicit, we'll specify demand as a fixed quantity, such as D overline. But we'll also discuss the case where demand cannot be met, and in that case, we'll need to think of demand either as explicitly or implicitly providing a willingness to pay function. So what do we mean by that? Well, when demand bids a function representing its willingness to pay, we'll interpret this function as specifying the derivative of its benefit function with respect to the power consumption level. So let's put the supply and demand side together. Problem 5.5 defined the economic dispatch problem. The offer-based economic dispatch problem is the same, and we repeat it here. We're going to minimize over choices of P the costs, F of P, which are the sum of the individual generator costs, subject to A P equals B and P overline less than or equal to P less than or equal to P overline. If we write SK for the generator constraint set, the set of feasible productions for generator K, then we can write this more compactly as the minimizer over for all K, PK in the feasible generation set of the objective F of P subject to the system constraint AP equals B, which will represent supply-demand balance. In section 5.3.1, we developed optimality conditions for this problem and for generators with convex costs and a specified demand. The first order necessary conditions I've exhibited here, I've repeated them. They involve Lagrange multipliers, lambda star, and Lagrange multipliers mu underline star, mu overline star, such that we have our first line of the optimality conditions that involves the Lagrange multiplier lambda star, which is the Lagrange multiplier on the power balance constraint, the Lagrange multipliers on the lower and upper generator constraints. The next two sets of constraints are complementary slackness for the lower and upper generator constraints. Then there's power balance, the lower and upper generator constraints, and then non-negativity on the Lagrange multipliers. As always, when I write capital mu, I mean a diagonal matrix whose entries is specified by the corresponding entries of lowercase mu. If we wanted to add demand bids into this formulation, the optimality conditions that result are quite similar. So let's do that and observe the optimality conditions including demand bids. To represent a demand bid, we need to define an additional entry in the decision vector that represents the demand. So the decision vector now consists of both the demand and the production decisions at all of the generators, P. We need to specify a feasible operating set for the demand of the form S0 is equal to, in principle the demand could be anywhere between 0 and D overline, and we'll then include an additional term F0 in the objective that represents minus the benefits of consumption. That is to say, we're going to modify the objective to be f of x is equal to F0 of D plus the sum of the productions at the generators. Our power balance constraint 5.4 is still that D is equal to the sum of the productions over the generators of PK, and now we're going to think of dispatching the demand just as we dispatched the generator. So let's see the resulting prices. We'll look at the Lagrange multiplier and power balance, look at an example, consider the case of no feasible solution, and do that by reinterpreting the case where not all specified demand is met as a demand bid. So as discussed in Chapter 7, by Theorem 414, the Lagrange multiplier lambda star on supply-demand balance is the sensitivity of the objective to changes in demand. As mentioned in Section 6.3, this sensitivity is sometimes called the marginal surplus, and it's the market clearing price. Our pricing rule will be to pay generators or charge demands for all energy uniformly at a price equal to lambda star. That is, energy is priced at the marginal surplus. Generator K is paid lambda star times PK for generating PK. If a generator is not at its minimum or maximum production limit, then the first order necessary conditions of the economic dispatch problem say that the generator K's marginal cost will be equal to lambda star. That's because the corresponding Lagrange multipliers, mu underline K star, mu overline K star, on the generator constraints are 0, leaving that the gradient of the cost function, in other words, the marginal cost, is equal to lambda star. A generator that's neither at its minimum or maximum is called marginal, and the pricing rule that we're adopting is also called marginal cost pricing. Sometimes we say that the marginal generator sets the price, although in fact all of the dispatched offers contribute to determining which generator is marginal, and therefore, in that sense, all of them contribute to setting the price. We'll also see that if a demand bid is not completely supplied, then its willingness to pay will be equal to lambda star. Paralleling the phrase for generators, we might say that the demand sets the price at its willingness to pay. We're also going to see that we can quite significantly generalize the pricing rule to the case where there's supply and demand for multiple commodities. The basic principle will be to price each commodity based on the Lagrange multiplier on the corresponding system constraint. Prices, again, don't depend directly on the Lagrange multipliers on the generator constraints. But of course, those generator constraints implicitly determine which generator is marginal and therefore determine which what sets the prices. Let's see an example. We had a previous example with 3 generators, D over line equal 3,000 megawatts, lambda star equal $50 per megawatt hour, and marginal costs of $40, $20, and $50 per megawatt hour. Let's assume that each generator sets its offer function equal to its marginal cost function. Then all energy will be transacted at a price of lambda star equal to $50 per megawatt hour. Generator 3, which is marginal, in other words, between its minimum and maximum, is paid its offer price, which equals its marginal cost. And we could say that the marginal cost of generator 3 sets the price of lambda star equal $50 per megawatt hour. Generators 1 and 2 are paid more than their offer price. They are paid more than their marginal costs. So in that sense, the marginal cost of generators 1 and 2 do not set the price in that their marginal costs differ from lambda star. But let me emphasize again that the marginal costs and capacities of generators 1 and 2 help to determine the economic dispatch, which of course then sets the price. I'll observe that demand pays at the price lambda star equal to $50 per megawatt hour. If there is enough supply to meet demand, then there'll be a feasible solution. However, if there are no demand bids or insufficient demand bids, and supply is insufficient to meet the specified desired demand, then there's no feasible solution. To put it simply, supply does not intersect the desired demand. This is an undesirable case. We generally don't want to be in this circumstance. However, we need to define what we're going to do in this case. From a practical perspective, the system operator must curtail some of the desired demand or perhaps violate some other constraints. We've only got a single system constraint at the moment of supply-demand balance, so it's not clear what else we could violate. But when we add in other constraints, then we could potentially consider violating them instead of the supply-demand balance. But let's suppose we do violate supply-demand. In other words, we curtail. Then we need to ask, what should the price be? Curtailment implies that not all of the specified demand can be served. Some of it has to be involuntarily limited. And we can notionally imagine a marginal disbenefit of involuntary curtailment, the value of lost load, or vol. We reinterpret the specified demand to be a demand that is bid with a willingness to pay equal to W, which we'll interpret to be the value of lost load. And we'll define a variable to represent the demand that's actually served. We've already seen this a few slides ago. Let's be explicit now, however, about the demand. For all D in the feasible set that allows D to be between 0 and D overline, the benefit of consuming D is equal to W times D. We require that 0 is less than or equal to D is less than or equal to D overline. That's our feasible consumption set. And there are corresponding Lagrange multipliers, mu underline 0 star, mu overline 0 star for these particular constraints. Figure 8.1 shows the benefit function, and notice that its slope is the willingness to pay, or the bid benefit. Let me repeat that the feasible set is S naught is equal to D in R, such that 0 is less than or equal to D is less than or equal to D overline. We modify the economic dispatch problem to include an additional term F naught that's equal to minus the benefit. And then we include power balance constraints now that are between the actual demand, might differ from D overline, and the actual generation. Well, if we go back to the first order necessary conditions, the first order necessary conditions corresponding to D is then given by 0 is equal to the gradient of F naught evaluated at D star, the optimal value, plus lambda star minus mu underline naught star plus mu overline naught star. Well, what is this gradient? It's equal to the derivative of minus benefit, and the derivative of minus benefit with respect to D is equal to minus W, because the benefit function is equal to WD. Lambda star is just lambda star, and we've also got the mu's. When the desired demand D overline is not completely met, then presumably D star is bigger than 0, unless we had a complete blackout, and less than D overline. So by complementary slackness, both of these Lagrange multipliers on inequality constraints are 0, and substituting that in means, and setting the first line equal to 0, we obtain that lambda star is equal to W. That is to say, the willingness to pay equal to W sets the price in this case. Generators should be paid and demand should pay at the price W. Let's turn to incentives. Going to need to make a significant assumption, the price-taking assumption. We'll look at profit maximization in this context. We'll then compare the offer versus marginal cost of production, discuss inframarginal revenues, and then finally a brief comment about investment decisions. We'll assume for now that each generator and each consumer of electricity cannot by itself individually influence the price. We say that each market participant is a price taker in the economic sense. As with many words in power systems and power system economics, the words have different meanings in different contexts. Price taker is also used in the context of an electricity market to mean a market participant who, for example, is at maximum capacity and therefore does not directly set the price. However, such a market participant can potentially influence the price and so is not necessarily a price taker in the economic sense. To be specific, we'll assume that the Lagrange multipliers from the ISO decision, the ISO problem, lambda star, mu underline star, mu overline star, that they do not change if any particular generator offer or any particular demand bid changes. In practice, they will change by some amount, so we're really assuming that they don't change significantly. We will then show that under the price-taking assumption, the pricing rule aligns private incentives to maximize profits with the public policy goal of achieving economic dispatch, that is to say, maximizing surplus. Let's repeat the analysis from section 5.3.4. We'll consider a particular generator that has a production cost Fk. If it produces Pk, then the cost of production is Fk. Let's suppose it is paid a price lambda star for its production. That is, the revenue is lambda star times Pk, and its operating profit is lambda star times Pk minus Fk of Pk. We ask, what should the generator K do to maximize profit, given that it cannot affect the Lagrange multipliers in the ISO problem? Well, given an energy price specified by lambda star, and assuming that the generator cannot affect lambda star, that means it's a constant, profit maximization involves finding a value of generation. Let me call it pk double star to distinguish this problem of individual profit maximization from the ISO problem, where I denoted it pk single star. Let's denote the solution of the following profit maximization problem by pk double star. Profit maximization is such simply maximizing revenues minus costs, subject to being within our feasible production limits. Equivalently, the generator could minimize the negative of the profit. Negative of the profit is costs minus revenues. And I'll observe that optimality conditions for minimizing this convex problem are that pk double star satisfy the following conditions: that there exists mu underline k double star, mu overline k double star, such that these conditions apply. So we could observe that generator K would seek pk double star, mu underline k double star, mu overline k double star that satisfy these optimality conditions. Generator K enforces its own generating constraints because its own problem will require the constraints to be satisfied. These optimality conditions for generator K, if we compare them to the first order necessary conditions for economic dispatch, for the ISO problem in other words, we'll find that these optimality conditions for generator K profit maximization are precisely the lines in the first order necessary conditions for ISO offer-based ISO economic dispatch that involve generator K. If we can assume differentiability and strict convexity of Fk, then these optimality conditions for profit maximization are uniquely satisfied by the particular values pk star, mu underline k star, mu overline k star respectively for the generation and Lagrange multipliers. That is to say, when paid at the price lambda star for all units of production, the generator making decentralized decisions to maximize its own profit given the price, that it'll choose to produce at the level pk star that's consistent with economic dispatch. The price, together with profit maximizing behavior by the generator, yields economic dispatch. The price lambda star, moreover, is a market clearing price, since total supply equals total demand. In the context of economic dispatch, this market clearing price is said to strictly support economic dispatch, meaning that there's a unique profit maximizing level for generator K, and this production level is consistent with economic dispatch. In some cases, Fk will be convex but not strictly convex, and there can be multiple choices that maximize profit. In this case, the choice of generation is not completely decentralized, since it requires specification of the value pk star by the ISO. However, amongst the various profit maximizing solutions, we'll discover that pk star, the ISO solution, is one of those profit maximizing solutions. In other words, setting pk double star equal to pk star will still be consistent with individual profit maximization. Again, the price is market clearing in that supply equals demand for some choice of generation and demand that's consistent with individual profit maximization. And to emphasize that the price is insufficient to determine the market clearing quantities, we say that the price does not strictly support economic dispatch. If we want to include the case of strictly supporting and non-strictly supporting, we could just say that the price supports economic dispatch. As it happens, several markets allow only piecewise constant offers, and such offers correspond to convex but not strictly convex cost functions. So in those cases, prices will support, but they will not strictly support economic dispatch. So far, we have implicitly assumed that the offer of each generator is the same as the derivative of its cost of production. That's what led to the lambda star, mu underline star, mu overline star. And we then observed that given those offers, the generators maximize their profit by taking actions that are consistent with the ISO solution. But we have not yet argued why the generator would choose to make an offer that's the same as marginal costs. Such an offer, by the way, is said to be competitive or price-taking in the economic sense. We need to explore the conditions under which it is profit maximizing to actually make a competitive offer. So let's continue to write X star, lambda star, mu, underline star, mu, overline star for the solution of economic dispatch based on the true marginal costs. But let's suppose that generator K specifies its offer to be different to its actual marginal cost. So instead of specifying an offer equal to the gradient of Fk, it specifies its offer to be gradient of Fk plus E. Again, gradient Fk is the true marginal cost. But E is a function representing the markup. On the other hand, it could be a markdown if it were negative of the offer above generator K's marginal cost. Since offers are supposed to be derivatives of convex costs, this modified offer must be non-decreasing. And the ISO uses the modified offer, gradient Fk plus E, instead of gradient Fk in its economic dispatch calculations, and possibly it'll get a different dispatch quantity X. We will nevertheless continue to assume that the resulting Lagrange multipliers, lambda star, mu underline star, and mu overline star, that satisfy the optimality conditions do not change even though we change the offer. We need to discuss the conditions under which this is true. But for now, let's just assume it. And furthermore, let's just pretend that the ISO's solution to economic dispatch with the changed offer would now involve generator K producing a changed quantity. Let me call it pk triple star. That's different to pk star. Well, by the same argument, same discussion as in section 8.11.2, we know that in fact pk star maximizes the profit for K given the price lambda star. So dispatching at pk triple star could not possibly have improved the profit compared to dispatching at pk star. Might be no worse than pk star, but changing the offer, if it didn't result in a change in prices, cannot possibly improve the profit. Well, if we don't want to therefore change the offer, we don't want to change the generator level that K is asked to generate at, how can we guarantee that? Well, the most straightforward way is to set E, the deviation of the offer from marginal costs, equal to 0. That is to say, the generator does best by offering at its true marginal cost. A similar offer applies for misspecification of minimum maximum capacities for power production. However, the corresponding results are somewhat weaker. We'll again suppose that the Lagrange multipliers in the ISO solution of economic dispatch are not affected. Then if we have a generator that specifies its offered capacities differently to its actual capacities, I claim will not experience better profits, at least in expectation, compared to the case where it behaved by specifying its limits correctly. Let's see a few cases to understand why this is true. As a first example, suppose that a generator physically withholds by specifying its offered capacity less than its actual capacity. Economic dispatch might have asked for it to operate at its offered capacity. Then it will receive a price at or above that offer price. But notice that if it had in fact offered in a slightly higher capacity, if it had made its offer capacity higher, it would have made at least as much or more profit by generating at a higher level at that same price. Remember, we've said that the prices are not, we're assuming that the prices are not affected. So reducing the offered capacity means you just get to sell less. You don't get to make as much profits as you could as if you had sold more. On the other hand, let's suppose that a generator specifies its offered capacity more than its actual capacity. If it's then asked to generate at its offered capacity, which is more than its actual capacity, it will be unable, in fact, to generate physically at this level. The implications depend on whether we're talking about a forward market, for example, day-ahead market, or a real-time market, which we'll explore in Chapter 11. If the market is a forward market, then the generator will have to buy back the energy it can't produce, and it'll have to buy it back from the later market. The generator risks that the price will actually be higher in the later market than it was in the earlier market. It's effectively made a virtual offer for the difference between its offered capacity and its actual capacity. It's selling generation that it doesn't have and agreeing that it will buy it back at any price in the real-time market. If all else is equal, there will typically be less supply in the later market because the generator that was apparently here in the early market is just not available in the latter market. So we will generally expect the buyback price to be higher in the later market. The deviation penalty then might be assessed if the deviation is large enough. So if the generator cannot actually produce what it agreed to and it fails to produce that in a real-time market, then it will be assessed a deviation penalty. And that might be key to the economic cost of procuring energy at late notice. So in either case, the generator either doesn't do better off or in expectation does no better. We'll further discuss the implications of misspecification and capacity in the context of reserves. I need to be very clear. All of the arguments so far rely on the assumption that the offer of the market participant does not affect the Lagrange multipliers. In fact, if a market participant owns multiple generators, or if a single generator is large enough, then the Lagrange multipliers in the ISO problem, and hence the prices that result from that, are affected by the offer of the market participant. So in that case, the offers that differ from marginal cost can improve profits compared to offering at marginal cost. This is, by the way, a typical economics definition of market power. If you'd like some further details about it, it's discussed further in my market power course. I've put up the website there, but we're not going to treat this case in detail in this course. From now on, in fact, we will treat offers and marginal costs as synonymous, and then we'll discuss how to deal with the case when they're not. Another observation that I need to make is that the examples used throughout the course typically involve large generators relative to the size of the market. It's much easier to solve examples with a small number of large generators than an example with a large number of small generators. But in an example with a small number of large generators, the firms in such examples have a large amount of market power and would improve their profits by not offering competitively. In general, we can usually recast such an example by dividing the generators up into a larger number of smaller generators, each of which have similar costs. We can then typically expect competitive or close to competitive behavior. Now I want to look at the inframarginal revenues or operating profit. For simplicity, let's first suppose that a generator K has constant marginal costs. This constant marginal cost function is shown by the thick horizontal line in the figure. Let's assume that economic dispatch results in a power level for that generator K that is between its minimum and maximum capacity. It's at some level PK star that's below PK overline. I haven't shown PK underline explicitly here, but I'm assuming it's below PK underline. By first order necessary conditions, the gradient of Fk evaluated at PK star therefore has to be equal to lambda star. So we can put in lambda star as being this height. Ignoring auxiliary costs, the cost of production of just being in service but not having any net generation is zero, so that the total cost of producing it pk star is given by the integral of the marginal cost, which, given that the marginal costs are constant, is none other than the product of the marginal cost at pk star times pk star. But that marginal cost is equal to lambda star, so that gives me that the costs are equal to lambda star times pk star, which is in fact also the revenues. So the revenues exactly cover the operating costs. More typically, marginal costs increase with production, as shown in figure 8.3. Let's again assume that the no load or auxiliary costs are zero. Then what we'll find is that Fk of pk star by strict convexity is strictly less than the gradient of Fk evaluated at pk star times pk star. We can either observe that through evaluating the integral or directly by strict convexity. Again, that product is equal to lambda star times pk star, and that means that the revenues, which is the area of this rectangle, exceeds the cost of production, which is the area under this sloping marginal cost line between 0 and pk star. So again, revenues cover operating costs. In this case, they more than cover operating costs. If a generator is at its maximum production, then we know that the gradient is equal to lambda star minus the Lagrange multiplier on the capacity constraints, which is less than or equal to lambda star. Again, if we have increasing marginal costs, we'll find that revenues more than cover operating costs. So here's lambda star. It's above gradient of Fk evaluated at pk star, which means that the payment or revenue, which is this area, is more than the cost, which is the area under the sloping line. On the other hand, if a generator is at its minimum production, then the gradient of Fk evaluated at pk star will be equal to lambda star plus the Lagrange multiplier. And in general, that will be greater than or equal to lambda star. As I've shown here, pk star, the gradient at pk star will be somewhere here, and that will exceed lambda star. The revenue in this case, the revenue, this rectangle, then can be smaller than the cost function, the area under this sloping line. So in this case, the revenues might not cover the operating costs. In the context of unit commitment, this situation suggests that the generator should be decommitted. However, under some circumstances, the ISO might need to keep the generator committed. And in this case, it would need to pay what's called a make-whole payment to the generator to cover this shortfall. We'll discuss this later in Chapter 11. When the revenues are more than the operating costs, which is the case we observed in the first three cases, at or more, indeed in the second and third case I should say, we say that there are inframarginal rents or inframarginal revenues. In practice, there may be a non-zero value of auxiliary costs, and as with the case of a generator being operated at minimum, we'll typically deal with non-zero auxiliary costs with a make-whole payment. Well, in the cases where there are inframarginal rents, you might ask yourself, why allow for inframarginal rents? There are a couple of answers to this question. First of all, the generators have capital and other costs in addition to the operating costs. And if the market price did not cover more than their operating costs, they'd all go bankrupt. The second answer is that, let's suppose we wanted to reduce payments. Maybe we were concerned about market power, and therefore we thought about changing the pricing rule so that each accepted generator was paid only what it offered. We'll continue to dispatch in order from low price to high price offers, and we still expect a similar highest accepted offer price, because that will still correspond to the generator that was marginal previously. But in such a so-called pay-as-bid or pay-as-offer market, the previous argument about a generator maximizing its profit by offering at its marginal cost is no longer valid. The reason is that it now, through its offer, will affect the price that it's paid. Each accepted generator will therefore want to forecast the highest accepted offer price and offer at that price or just slightly under it in order to maximize its profits. There's a result in economics called the revenue equivalence theorem that suggests that changing the pricing rule will not result in changes to the net payments. And the basic reason is straightforward. The offers will change in response to the changed pricing rule. So the payments under pay-as-bid or pay-as-offer will end up matching the payments under the uniform pricing rule. Unfortunately, the revenue equivalence theorem has conditions, restrictive assumptions that do not exactly hold in electricity markets. However, the result approximately holds. And as a general observation, changing the pricing rule is unlikely to significantly change the revenues. Furthermore, under a pay-as-bid mechanism, the profitability of each generator depends on each generator forecasting the price and offering at that market price. Due to imperfections in forecasts, however, these predictions will be wrong and will get poor dispatch. You could imagine, for example, a nuclear generator who forecasts high prices and, on the other hand, a gas plant that forecasts low prices. All electricity markets in North America set prices based on the Lagrange multiplier on supply-demand balance as we've described here. They typically, however, have varying approaches to pricing under scarcity, that is, occasions when not all desired demand can be met. Finally, let me just mention something about investment decisions. As discussed in Chapter 7, if generators and generator infrastructure come in small lumps, do not exhibit economies of scale in construction, can be built quickly, and if no participant can unilaterally affect prices, then investors have the incentives to build the right amount of generation capacity. If there is too much capacity, then prices and anticipated prices will be low. Inframarginal rents will be small. There'll be little incentive to invest in more generation because it simply won't be profitable to build new generation. On the other hand, if there's too little capacity, then prices will rise until inframarginal rents are large enough to encourage new investment. Investment in peaking capacity will only occur if demand sets the price at peak, as we discussed in section 7.8.15, or if there is some other mechanism to allow peaking generation to cover more than operating costs. For example, a capacity market. If prices are depressed, for example, by market power mitigation rules, then investment in peaking capacity will not occur spontaneously. That completes the basic discussion of offer-based economic dispatch, but there are a number of additional topics to discuss.